My name is Sean from University of Technology, Sydney. First of all, I'd like to thank you, Professor Matsuyama, to invite this IWMK workshop. Also, thank you, organizing committee, for the hard work every year. So today, my talk is about the inkjet printing technology on depositing nanomaterial for thin film composite membrane fabrication. So I'd like to thank our co-authors, MJ Park, Chen Wang, and Michael, most for experimental data, and then they also contribute a lot for this study. So this is my outline for this talk. So I just want to briefly mention about our university and our center, and then background why we want to do inkjet printing, because everybody use printer to print out your materials, and then we just want to change to the membranes to modify your membrane surface. So how this will make a very cost-effective and simple way, and how to apply for inkjet printing technology in nanofiltration, fabrication, and modification. First, I want to explain the inkjet printed single well, the carbon nanotube as an interlayer for nanofiltration membrane. The second topic is surface modification of polyamide nanofiltration membrane via inkjet printing of the graphene oxide. So we use the CNT and graphene oxide to improve the overall performance of the nanofiltration for the application of organic solvent nanofiltration, as well as the general BWRO for wastewater reuse and desalination. And try to conclude my presentation. Our university is located in the city of Sydney, so we are very much close to Opera House. So if you have opportunity to visit to Sydney, and then please come to our university. And we have 45,000 students. Our center is mainly focused on water and resource recovery, and also general green environment technology. So we have 20 staff, 10 research fellows, and 75 PhD students. So our center is located in Faculty of Engineering building, which is one of the most green star building in Sydney. And we have membrane activity to fabricate the membrane distillation, food osmosis, organic solvent, nanofiltration, and pressure retardant osmosis. So Myung-Jun Park, Chen Wang, and Nashad, and Jerry Ren is contributing this area to develop the high performance of membrane for desalination and organic solvent separation. So you can see the electrospinning and 3D printing membrane, also flat sheet, the thin film composite membrane, also hollow fiber membrane to make the microfiltration, ultrafiltration, as well as the osmotic membrane. So we try to utilize the different polymer and surface modification, especially nowadays we are working on the polyketon, which can be useful for organic solvent nanofiltration, as well as general application of microfiltration for osmotic membrane bioreactor. Also mixed membrane with nanomaterials, modification of membrane support or selective layer using nanomaterial. So we try to produce the best performance of the thin film composite nanocomposite membrane. Also, we are trying to make resource recovery from urine and wastewater, as well as lithium for the rare earth material. So one of the examples is our building consists of the waterless urinal. So we collect the urine from toilet, and then we try to apply for the membrane bioreactor produced from our laboratory, and then go through the membrane distillation to further concentrate our urine to convert to fertilizer, and then apply to our green water system or urban farming. So we generated our trademark of the urban. you are valuable or urine is valuable. So we try to contribute agriculture using membrane technology to make a compact and then very effective way of the resource recovery from your collected urine diversion system. And then we want to have more commercial opportunity to make this resource recovery to make urine to fertilizer solution. So let's get to the point for today's my main topics, inkjet printing technology and its application. So already you know the inkjet printing. So from Hewlett Packard or Sony, many different companies, they produce the inkjet printing and they utilize the inks. And this is the nozzle spinneret. And you can see the micro droplet from your black ink or red ink, different colors, and goes to your paper on the paper, and then you can produce your inkjet printing system. So if we apply this system to membrane fabrication as well as the modification, what could be advantage will be low production cost and precise deposition control of materials such as nanomaterial and functional polymers, and relatively simple, fast, and scalable method for material deposition, minimally consume the deposit material, easily adapted to a roll-to-roll process, suitable for large-scale production. So if you look at the application, electronics, graphics, displays, optical, life sciences, photovoltaic. So when you need a very precise surface modification, so we can apply for inkjet printing. So why not? We can utilize this system for our membrane technology because a lot of people are producing nanomaterial, new polymers, new functional material every day. So we can try to combine with this inkjet printing, which is very simple, and then which can control for your useful material to membrane technology. So we published one paper together with Professor Matsuyama this year in JMS, the inkjet printed single-wall carbon nanotube as an interlayer for high-performance thin-film composite nanopenetration membrane. So we tried to apply for OSM membrane. So how this membrane can be produced. So we just utilize the very simple, the inkjet printer, just $100. You can buy from your electronic shop, and then we just change your cartridge filter to convert your CNT inside your cartridge, and then print on your membrane surface, and we produce the surface modified OSM membrane and characterize how we improve the performance and then overall mechanical strength. So we just want to explain this publication. So ideal thin-film composite membrane structure, very ultra thin, and then defect-free mild layer for highly efficient ion and molecular sieving with the minimal water transport resistance, and require the support membrane with carefully crafted pore structure and the surface properties, which has high porosity, uniform, small and narrow pore size distribution, smooth surface, and hydrophilic surface property, which will lead to the homogeneous aqueous solution distribution and homogeneous monomer diffusion during IP process, enabled to control the polyamide layer. So we look at the previous literature, and then we found out one interesting paper published in very high impact journal Science, and they mentioned about sub 10 nanometer polyamide nanofilms with ultra fast solvent transfer for molecular separation will have very good your overall performance of the membrane. So Andrew Livingstone discovered that the thickness of the polyamide at 10 nanometer achieved ultrafast solvent permeance without decreased membrane selectivity by the controlling IP process with utilizing nanostrand interlayer. So this is their study. So you can see the support layer for general ultrafiltration like a PSF or PES, and then nanostrand layer. So they utilized some nanostrand layer in this interlayer system between support layer to your selective layer. And then selective layer is very much typical polymerized nanothin film at the surface like MPD-TMC or PIP-TMC, and then try to separate some of the organic solvent. So this is their study. They found less than 10 nanometer, ultra thin. The polyamide layer will give very high performance of the solvent permeance. That's our inspiration. We try to control this polyamide very thin film layer, and then see how we can better separate the organic solvent. So if you look at the different nanomaterial, we have selected SWCNT, interlayer deposition. And previous study, they tried to utilize the vacuum filtration system or the spray-coated SWCNT interlayer and move templated SW interlayer brush, just to simply brush painted SWCNT interlayer. So there are many different methods to coat your CNT as an interlayer, and the key trend of the deposition technique is coating for SWCNT on the substrate with the simple, easy, scalable approach for a large-scale production. That's the reason why we try to combine with this SWCNT with the inkjet printer. So this is the inkjet printing. We just purchased from the commercial laboratory, and then we purchased one inkjet printer, and then this is the cartridge. So we just mixed with our inkjet for the cartridge, and then we installed our inkjet and then tried to print our SWCNT and then see how we can perform. So this is our membrane sample. So you can see on the top of the PES MF membrane. So we just utilize our SWCNT interlayer, and then we try to compare how this improved the overall ultra thin polyamide. 10 nanometer was our target, but in fact our experimental data was not really possible to create 10 nanometer, but very much close. And then I want to share for next slide. Oh. Hello, can you hear me?
Yes, no problem.
All right.
Yes, no problem.
Because I have one video, so looks like this crashed this PowerPoint. So just to stop this software, let me try to show this printer. Can you see?
Yes.
Okay, so this is what we print our CNT on the top of the membrane surface.
Oh,
So it's very
Sean.
Yeah.
Oh, please show your PowerPoint. Now, your voice is okay, but
all right. So let me share again.
Yes,
It's
clear.
okay, right?
Yeah.
All right, because this video looks like. So let me try to play the video. Can you see?
Yeah. Yes.
All right, so you can see the membrane. We just utilize the SWCNT and then print one time, 10 times, 20 times, and then we look at the different way of their layer and then how this will change the overall membrane characteristics. So we just compare this result. So this is the 0 and 5 print 10 and 20 times. So when you increase the overall printing cycles, so you can see how this PS membrane changed. So you can see that all the CNTs blocked their pore size, and then overall their roughness it's reduced from 34 nanometer to 21 nanometer, and you can see how this color of the membrane. When you see the 5 times and 20 times, the black color also changed on the surface of the membrane. So based on the number of the printing cycle, we try to look at how this yeah. So this is the membrane property with respect to the number of the SWC and ink project. So when you have more cycle, the average pore size changed from 274 nanometer to 53, and then pure water permeability also changed to 4500 LMH per bar to 495, and then contact angle increased because of the carbon nanotube. So that's the overall membrane, the property. Also, we try to optimize the IP on the top of the CNT layer. So we utilize the PIP and then TMC IP condition, and then different concentration. PIP were used to 0.05 to 2.2 weight percent, and TMC was fixed to 0.1 weight percent of hexane. And then we tested the membrane performance, and then this is our result, permeate flux, and then sodium sulfate rejection in terms of PIP concentration. So if you see the overall flux, the black color, and then blue color is the rejection. So rejection increased and 0.15 the PIP concentration, and flux is very much also stable. When you have print 10 times at this 90 mH per bar, so we select the optimal condition, 0.15% of the PIP concentration, and then we compare the different printing method. So PA layer with different SAM, so you can see how they changed the cross section. So initially, you remember we targeted 10 nanometer of the polyamide, which will give a very high permeance from the previous year's literature. Then when we had zero printing, you can see the 125 nanometer of polyamide layer we identified, and 5 prints, 95 started decreased. So when you increase the cycle of your printing, so finally 47 nanometer, even though we was not able to achieve the 10 nanometer of the polyamide thin layer. However, definitely we try to reduce from 120 nanometer to 41 nanometer. And then we look at the overall performance, whether this shows the better rejection and water flux. So this is our polyamide layer. So uneven coverage for PIP without any interlayer of the CNT. And then it should be looks like PIP and TMC, they have IP on the polyamide, which will create the higher thickness. On the other hand, when you combine with the SWCNT, the interlayer try to cover it up on the support layer of the microfiltration or ultrafiltration, and then we can control the ultra thin and defect-free polyamide on the top of your CNT interlayer system. So that's our proposed mechanism, and we look at the next slide. What's the permeability and rejection depending on our So let me stop sharing again, and then it looks like my PowerPoint is too heavy to So yeah, this is our overall performance. So we found out when you have different cycle, and then permeate flux, and then sodium sulfate rejection. So you can see the different same images from the 10 to 15 times. So we achieved around 97.88% of rejection, and the highest flux of 18.24 LMH per bar. And this is what we compared with the control. Then we improved almost double of the water flux. Then rejection improved almost 5% compared to the control membrane. So this is our overall performance of the printed membrane. Also, we look at the different salt removal and flux variation. So we found out the sodium sulfate is highest rejection, followed by the magnesium sulfate, magnesium chloride, and sodium chloride. And then the potential also gave us good insight for synergistic effect of the molecular side sieving and then strong donor exclusion effect with the sulfate salt. And long-term experiment, and then very stable water flux, and then our rejection. So we found out that this printed membrane shows the good potential to modify your overall membrane surface characterization. So this is summary. A high performance TFC NF membrane with ultra thin PA active layer was successfully synthesized using CNT as an interlayer, and SWCNT ink printed over 10 cycles efficiently modified the surface morphology of the PS support membrane. And the CNF membrane fabricated at the optimal condition exhibited significant improved membrane performance, including the water permeate flux and rejection. And this is the overall OSN application, and also we look at the different application. So we try to see how we can make anti-fouling and chlorine resistance membrane using graphene oxide coating using this inkjet printing. So this is background. In general, people try to make a surface grafting, decoating, and incorporation of nanoparticle layer by layer. And challenges are controllability versus scalability, and the waste expensive chemical and nanomaterial. So synthesize the novel PDA, geoprinted nanofiltration for wastewater, and investigate effect of geoprinted layers and effect of the geoprinting layers on membrane performance in terms of permeate flux, salt rejection, as well as the anti-fouling and chlorine resistant property. So this is very much similar I already explained. We just changed the graphene oxide in the inkjet cartridge, and we just printed out this material with the graphene oxide, and then different cycle, how this changed the overall performance of the membrane. So this is the graphene oxide. We have 1 times and then 3 times print. And then you can see the control, and then they changed the morphology, also changed to the contact angle from 81 to 66, less hydrophobicity. And then thickness of this roughness is changed also 44 to 23 nanometer when you have more cycles of the graphene oxide layer. And then we try to compare what's the overall performance change of the permeate flux and rejection. And you can see the flux was initially 13 LMH per bar. And then when you have inkjet printed geo, and decreased a little bit of overall flux. On the other hand, increased your salt rejection, which is the general trait of the permeability and selectivity. Then, based on that, we look at also different membrane fouling effect. So you can see what's the normalized flux in terms of different cycle of the geo inkjet printing. So we use the BSA, which is the very typical membrane foulant, and we found out this is control. So decreased almost 50% of fraction without any inkjet printed geo coating. However, when you have 3 times the geo coating, so only 20% of the reduction of the overall your performance. Also, we tested their membrane fouling recoverability, and then they have better recoverability when you have a geo coating material compared to the control. And this is the chlorine resistance. We utilized the previous literature. They utilized the 6,000 ppm for sodium hypochlorite for chlorine resistance experiment. So this is control. And then our geo printed membrane on the surface. And then we tested 0 to 3 hours. So you can see the overall their control, the rejection decreased because exposed to the chlorine. And then rejection decreased, which means the membrane is damaged because of the chlorine, from 90% to 86%. On the other hand, our graphene oxide PDA printed membrane shows the very consistent way of the rejection. So we can also summarize PDA printed nanofiltration membrane exhibited higher salt rejection while achieving the slightly lower permeate flux. The PDA geo-printed membrane exhibited enhanced anti-fouling properties. And PDA Geo3 and membrane showed better chlorine resistance compared to the control membrane. So I'd like to thank you for the funding organization, Austrian Research Council Discovery Project, also our co-author, Michael, Chan, MJ. Thank you for your attention.